Um, Good morning, everyone. My name is Renato Gomidi. I'm a master's student at Federal University of Goiás. I'm a pleasure to welcome to this session presented by Zerihun Tadesse. Dr. Zerihun Tadesse is a wet breeder at CIMMYT in Kenya with over a decade of experience in wet genetics and breeding. He integrates field phenotyping, half cycle, genomic selection, and marker-assisted breeding to development high-yielding, disease-resistant, and climate-resistant wet varieties tailored to resource-constantly farm across the Africa. His primary focus is rust resistance, breeding, and disease phenotyping, partly for sting and yellow rust in West African hotspot environments. Driven by strong commitment to food security, Dr. Tadesse wet breeding strategies to prioritize the need of small farmers, aiming to enhance productivity, sustainability, and nutritional quality through the region. Before we begin, I'd like to remind everyone we have a Q&A session at the end of the lecture. Please feel free to submit your questions and comments through the chat, the presentation. Dr. Tadesse, it's a privilege to have you with us today. On behalf of the organized commitment and your audience from around the world, thank you for very much for sharing your time and experience with us. You might begin.
Okay, thank you very much. Good morning, good afternoon, and good evening, wherever you are connecting for this seminar. It is my pleasure just to be part of this seminar and just to share my experience and our CIMMYT work in Africa just for the audience. So, my name is Zerihun Tadesse. I'm working for CIMMYT. Based here in Kenya, Nairobi, Kenya. So I will give you some highlight on the harnessing genotype by environment interaction for climate resilient and rust resistance wheat development in Africa. So one second. Okay, so this is my presentation outline. So I will give you a little bit introduction and background information about CIMMYT with breeding program because I've seen the previous years of this G by E day, and then I never seen any participant from CIMMYT. So I will give you some background about our breeding program, and I will give you also what is rust and how it's important in Africa, especially, and what the African wheat breeding pipeline looks like. And also, I include some case study that's linked with genotype by pathogen by environment interaction that will give you some idea about how this interaction is very important just to get ideal genotype for the resource poor farmers and collaborative breeding pipeline for impact. I will give you some highlight about that also, and lastly, the take home message. So what you are learning and what is the key message from this presentation. So as you all know, just maybe if you are not new for wheat, around 220 million hectare cultivated across globally, and almost proportional of the land is in developing and also developed country. So out of these 220 million hectare, CIMMYT is targeting, our breeding programs targeting around 65 million hectares of land, especially in Asia, Africa, and Latin America. So as you can see from the map, those green highlights are our target environment, and then our breeding also dealing with those agroecologies just to deliver high yielding wheat varieties. And as you can see on top of the map, these are some of the main traits now we are dealing with, like high yielding, quality, disease, and also heat, stress, and nutritional quality. These all are our breeding objective. We are working just to get ideal genotype for different product. Just to give you also some introduction or overview of the CIMMYT wheat breeding program evolution. It started in 1944, established by Norman Borlaug. I think everyone knows this name. It's a Nobel Peace Prize winner and also the father of Green Revolution. So it started in 1944 in Mexico, and then after there are a lot of different steps going on until today, and some of them are including like shuttle breeding program. The idea of shuttle breeding program is just to growing wheat twice in a year in different location. For example, in this case, we have a location called Obregon in Mexico, and also we have a location called Toluca in Obregon in Mexico. So these two environments are completely different, and they are very contrasting environment. So by shuttling the material within these two location, Norman Borlaug achieved just to develop wide adaptable varieties to the farmers. And also the Green Revolution in 1960, that's mainly related with the semi-dwarf wheat genotype, especially in the Southeast Asian country. And after that, also materials distributed across different areas of the country just to benefit small scale farmers. And in 1980 to 1990, mainly targeting on durable rust resistance, because rust is a major bottleneck for wheat production across globally. So that's one of the target trait starting work in CIMMYT wheat breeding program. Since 2000, we are also starting working on the quality and nutritional aspects, especially the micronutrient, that's zinc and iron. These are the hidden hunger of most of the target environment. So now CIMMYT is integrating this zinc and iron breeding program into the mainstream breeding pipeline. And starting from 2010, we are also integrating molecular genotype data just to get a good prediction of the lines. And also we used high throughput phenotyping just to increase the data point for decision making. And starting from 2020, just we also integrate in our breeding program the speed breeding facility. So the idea of this speed breeding facility is just to accelerate the generation cycle, which is the main driver for the genetic gain in the breeder's equation. So this speed breeding facility already integrated in our breeding pipeline just to accelerate the generation cycle. And this year we also start the hybrid wheat program. So just to explore the heterosis of wheat into the small scale farmers. So this is starting just we start this year. So I hope we'll have some product very soon. So this is in short the history of wheat breeding program in CIMMYT. So when we breed, just we are not breed something, for everything. So there should be some target agroecologists. So there are different histories in our breeding program. For example, in 1970s, there was like 50 agroecological zones we are targeting in our breeding program. And then we reduced this one into 12 in 1988. And after that, we are just doing some calibration and also optimization just to get exactly the mega environment. And starting from 2021, we already start the target population environment concept, which means again just to split or subclassify the agroecologists in different target product pipeline. That is the main idea of exploiting genotype by environment interaction for specific adaptability instead of just having one genotype serving the whole different target population environment. So based on that classification, now in CIMMYT we have 5 breeding pipeline. So all those breeding pipelines serving for different agroecologies and also different areas. So as you can see, pipeline 1 is mainly focusing on Central Asia, South Asia, West Asia, North Africa, Sub-Saharan Africa, and Latin America. So under this pipeline 1, there are a number of target population, target product profile concept. So all those target product profile concept serving for different target regions. The same thing for pipeline 2, 3, and 4. And then pipeline 5 is mainly focusing on Africa. Still, we are focusing in West Asia, Latin America, and Central Asia. But the majority of the targeting agroecology for this pipeline is the Eastern Africa, and then some of the effect also going the other part of agroecologists. So this pipeline 1 and pipeline 3 is mainly focusing on high yielding and also medium to long maturity group of wheat genotype. And pipeline 2 and then pipeline 4 is mainly focusing on high yielding but short period of short cycle or early maturity group of wheat genotype. And pipeline 5 specifically more focusing on the disease package, because this pipeline is, as I said, more focusing on East Africa, and East Africa is mainly known by different disease factors. So our target is mainly just to develop high yielding wheat varieties with a good level of resistance. So how we are doing the breeding? So my presentation is mostly, as I said, just the application of how G by E, because the previous presenter already, Professor Fred, he already mentioned how the concept of G by E and also how we classify or subdivide the different source of variation just to explore the G by E. So my presentation is entirely focusing on how we apply that one in which breeding concept. So this is how we do the breeding. So we have two major components. We call it population improvement and also product development. So for population improvement, we are recycling material as quick as possible just to accumulate favorable alleles just for different traits. So as you can see, we have crossing, advancing. So when we are advancing our material, we are doing a number of selection criteria and then line extraction. Then after we genotype our material just to predict GEBVs or for selecting material for the first stage 1 testing. Then after stage 1, we advance that one into stage 2, stage 3, and then finally we distribute that one into international nursery. So in this exercise, we are also integrating molecular marker, high throughput phenotyping, speed breeding, and also, as I said, we're also working on the nutritional aspect of the wheat. So there are two parts, as I mentioned, population improvement and product development. So when we are saying population improvement, mostly we are focusing on the base parent. The base parent may not be the best product, but the base parent maximize the number of favorable alleles across all target traits. So we have a number of different target traits we are focusing. So when we are selecting the material or a parent for our crossing block, always we need to use the base parent, maybe not the base product. And in the other side, when we select the best product, that means a material meets at least the minimum threshold for all breeding traits required in target product profile. So these are the combination of our breeding activity. So this will explain the entire operation starting from the crossing up to product development or product release. Oh, sorry. Yeah, so this is almost the repetition of the previous slide, but just to give you more detail about our operation. So when we have the first crossing block, always we are looking elite by elite. So this is a main breeding pipeline, so it's not a pre-breeding. So always we are selecting elite by elite combination. So when we are advancing in different generation, for example, F1 advancement, we don't have any selection activities, so we use speed breeding just to advance the material. And F2, most of the time we are using marker as selection just to select the best lines for next generation. And mostly we use also the feed selection, especially for disease. And at year 3, mostly we use genomic selection just to do the negative selection or culling down the lower GEBV values of the lines, and then we advance that one into stage 1 trial. So after stage 2 and stage 3 and then seed multiplication, we distribute our material into different partners in the world. So how we do this multi-environmental testing? Once we have fixed lines, how we do a test and select the best line, or we call it stable or high yielding material for international nurseries. So we have 6 simulated environment in the field in Obregon. So Obregon is our main breeding station in our breeding program. So there are 6 simulated environment. So the first 2 environment, we call it bed 5 irrigation, which means 5 means 5 times irrigation. So bed and flat kind of planting strategy. So this represent the high potential environment. And also we have bed drought drip, which means entirely using the drip pipeline just to monitor the amount of water, and also bed to irrigation, which means only to irrigation from planting to harvesting. So this represent the drought environment selection. And the last one is bed early heat and bed late heat. That's also related with the heat. And then we are exposing early heat or late heat in the selection process. So as you can see from the picture, bed 5 and flat 5, the high potential environment looks perfect, and then we are expecting a yield of more than 8 ton per hectare from the plot. But when you are considering bed drought drip irrigation and B2 irrigation, it's almost 3 to 4 maximum. So there is a yield penalty, but still that give us a very good indication which line is performing across the drought environment. And at the same time, for early heat and late heat also, that give us which line is more ideal, or which line is more tolerant for early heat or late heat. So these 6 environment we use just to evaluate our material before we are distributing to different agroecologists. And then we have also target population environment, especially now we are working this in South Asia and also in East Africa. So the idea is just to send early material just to see how this material performing, and just for selection purpose, and also just to do some correlation. So as you can see here, all this testing scenario will give you a good indication for yield potential evaluation, especially the bed 5 and flat 5 irrigation, heat stress phenotyping, the early and the late heat trial, and water use efficiency that related with the B2 and BDRT, which means bed drought drip irrigation. So the amount of water is very small, 180 and 120 millimeter from planting to harvesting. So this environment, selection environment, will give us a very good indication. But one of the missing component here is the disease resistance. So once you have once we have a very good line, if it is susceptible, that line may not be advanced as a variety release, especially when you are considering resource poor farmers. So for this purpose, for disease resistance, we were working on the shuttle breeding strategy. In addition to Obregon to Toluca, we have also shuttle breeding program between Kenya and Mexico. That gives a lot of advantage, especially for selecting material as early stage for disease resistance, especially in Kenya's stem rust and yellow rust. So that will give a very good indication at early stage just to remove those susceptible lime from the population. So that's one of our strategy just to get a disease resistance genotype. But this strategy already stopped due to the rapid generation advancement, which means in this scheme, it takes around 7 years just to distribute a material from crossing up to international nursery, which means it's a lot of time, 7 years. So we reduced that one in 5 years by excluding the shuttle breeding program with Kenya. In that case, there is no mechanism just to test our material for stem rust or yellow rust in the field. So that's why this Eastern Africa breeding pipeline established in Kenya. The other most interesting part also when we see this sixth environment, the simulated environment, as I mentioned before, in Obregon, as you can see, there is low to moderate correlation between different selection environment, and that indicates substantial genotype by environment interaction, because we are testing that one in the same area, but different water, different temperature, and different planting scheme. So as you can see, there is low to moderate. We have not seen any strong correlation even between the two potential, or the two moisture stress, or the two heat tolerant kind of testing environment. So that clearly indicates us there are a unique correlation pattern, confirm that selection environment represent different target population environment. So that's a good platform for us just to screen our material and just to get a very good genotype that represent different target population from this selection environment testing scheme. And the other one is variable correlation across years, highlight the importance of multi-environment testing, because as you can see, even between across years, we don't have a consistent magnitude of the G by E interaction, or consistent magnitude of correlation between different selection environments. So that indicates or pushes how multi-environment testing is very important. So for your reference, if you want, just you can read this improving with grain yield genomic prediction accuracy using historical data. That will give you a little bit information about our selection environment, and also how that historical data increase the accuracy of genomic prediction in our breeding pipeline. So after this all, just we distribute our material in different part of the world. As you can see, in developing or developed country, public sector or private sector, there are a lot of institutions. They are using our germplasm as a breeding line, or their direct release for their breeding program. So this elasticity or adaptability comes from all those selection environment activity, and also the target population environment testing scheme. So that gives more elasticity or more stability of our germplasm and performing in different part of the world. And as you can see here, also there is a genetic gain, because without genetic gain we are not doing anything. So we need always increase of yield per unit area. So as you can see in our selection environment, like bed 2 irrigation, bed 5 irrigation, and bed late heat temperature trial, as you can see from the 2070 to 2025, there is a genetic gain increase per year for the three selection environment. They are representing the three different traits. And also, as you can see, the distributed line across different part of the world since 2004 to 2016. As you can see, there is increase of yield ton per hectare, which means almost close to 65 kilogram per hectare per year, which represent around 0.96% of genetic gain from our breeding pipeline. But we are looking more than that, more than 1.5 sometimes, just to increase the wheat production across the globe. But this is from our nurseries, what we are distributing to different part of the wheat growing environment. So the major question now here, do we only need high yielding and stable wheat genotypes in different part of wheat growing agroecologies? So this is the main question, and we need to answer before we go to the second part of my presentation. So the simple answer is no, because especially in Africa, the scenario is completely different, that link with different biotic and abiotic stresses. So we need something to explore uh, local adaptation or specific adaptation of the genotype by environment interaction. So just to give you a little bit continental context of the wheat in Africa, I think Africa is importing a lot of wheat from different part of the world. And as you can see, a total production around 25 million tons from the 10 million hectare, which is very small, which shares around 4.5% of the global wheat production. But Africa is sharing around 25% of the total global population. So the production of wheat is very, very low compared to the demand, and more than 46.4 million metric ton wheat is every year imported from the other world just to fulfill the demand. So region-wise, North Africa consumes a lot compared to the other part like Southern Africa, but all the regions require wheat every year, wheat import every year. So in the right side of the slide, as you can see, the consumption and production trend, the consumption is increasing very dramatically as compared to the production. Except Southern Africa, the whole region is different kind of increase in terms of production, but the consumption wise, almost they are similar. There is high demand of wheat in every year. So Africa really needs a lot of wheat production just to fulfill the local demand. But there are a number of other factors that affect the wheat production in Africa. So as you can see, I will not just go through all, but biotic stress is the major and a very unique part of the region. So as you can see here, climate change is there, but involving pathogens, especially stem rust, stripe rust, and other like Fusarium, red blight, and Septoria, they are the major wheat production limiting factor in the region. But there is also a potential in Africa just to increase the area, the production by integrating genetics and agronomy, and also expanding wheat area in the irrigation and drought tolerant variety by using drought and heat tolerant varieties. And also national policy is very, very important just to achieve wheat self-sufficiency. So why wheat rust is important in Africa? But not only in Africa, rust is very important across the globe. As you can see the map in the right side, the upper and the lower, just wheat, stripe rust and stem rust is very critical, and it's depend on the area. But in Ethiopia, for example, as you can see in East Africa, Ethiopia and Kenya specifically, both stripe rust and stem rust is very, very important. And also they are causing a lot of wheat reduction. And the map shows the UG99, one of the most aggressive type of pathotype in stem rust pathogen. So that's the how it's distributing across the eastern and southern Africa, and also move to the southern Asian countries. So just to avoid and just to get a lion having a very good level of resistance, not only for stem rust, for different diseases, our breeding program is having a global disease phenotype network across different country, as you can see. And then we are testing our material for different pathogens just to evaluate and then use those material for the breeding purpose. So in Africa, especially in East Africa, in Ethiopia, we have a screening platform in we call it Dabrazate, that's for stem rust. And also in Kenya, Nijoro, we have a stem rust screening facility, especially for the UG99 race and its derivative. But we have also in South Asia for yellow rust, in Mexico for leaf rust, yellow rust, and non-UG99 type of stem rust screening also going on in Mexico. And for Chile, we have yellow rust, and also for Uruguay, we have leaf rust, septoria, and fusarium head blight screening platform. So this all gives us a very good data point for our selection decision. So recently, as I mentioned before, we don't have any more shuttle breeding program between Mexico and Kenya. So what we are doing when we have stage one line, which is close to 4,500 lines, we are testing this material in Southern Asia, especially in India, and also in East Africa, Ethiopia, and Kenya, just to see how those selected material is responding for different disease. So this is how it looks like in Kenya stem rust, and also in stripe rust in Ludhiana, India. So based on this all combined information, we are advancing our material into stage two stage. But there is a high G by E by Y effect for rust, especially stripe rust. For example, this is one of the study using the Vavilov and Ethiopian wheat population, around 388 breed wheat lines, including this study. And as you can see, the trial genetic correlation, there is a very clear clustering pattern based on the year. So as you can see, all the trial conducted in different within a year, they are clusters together, and between a year they are different. So what this tell us, there is something going on the rest side, in the pathogen side, because the same material but the same genotype in different location, but in different year. And when you see the genetic correlation, they are highly genetically correlated within a year, but they are low genetic correlation across the year. So that clearly indicates there is a pathotype shift across the years. That's why sometimes it's very challenging just to develop a material having resistance for a particular race, and then next year the other race evolve and it will broken the resistance genes. So as you can see from the global rest reference center, there is a shift of pathotype. We call it PST11. It was very dominant until 2090, but after 2090, there is a race shift from PSTS11 to PSTS16. That shows clearly in the genetic correlation of the multi-environment trial. So high genetic correlation within and low across testing years indicate a significant genotype by year effect. This suggests the presence of pathotype shift. So that will tell us clearly how it is complicated just to breed for stem stripe rust resistance. The other study also, just including Australia and Ethiopia, as you can see, there is a crossover interaction in terms of response of yellow rust for the genotype of response for yellow rust, between Ethiopia and Australia. At the same time, as you can see, the genetic correlation here as well between different continents, they are separately clustering. So this is also clearly tell us there is a big pathotype difference between Ethiopia and the Australian environment. The other one is for stem rust. For example, when we are developing material, we are also doing seedling testing in addition to adult plant stage phenotyping. So as you can see, between these 5 different stem rust paratype, there is a low correlation pattern, especially for TTK-TT, which is a very aggressive one and virulent for SR36 genes. So as you can see, very low correlation means there is a difference between the response of genotype for different paratype. So that's also one of the indication we need something having a broad adaptive resistance for different paratype. So how to breed for rust then? Just if we have this kind of issues. So this is a typical representative how we need to breed for rust just to decrease the susceptibility level. So as you can see, if you have only one gene or one or two minor gene, the susceptibility is very high. And if you have like 4 or 5 minor genes, the susceptibility is very low. So which means if we have a combination of different minor genes, which means the effect of or the susceptibility level is very low. So in general, a multi-environment phenotyping is essential to understand the G by E effect and identify stable resistance cultivar. So modern breeding integrate genomics that gives for prediction, and digital phenotyping is very important just to phenotype our material in the field quickly and also precisely. From the previous study, what we have seen when we accumulate number of QTL in different genotype, as you can see, the disease severity is going down. So for example, in the first plot, when you are accumulating more than 7 QTL together, as you can see, the level of the disease severity is very low. So which means QTL stacking demonstrate the additive effect of multiple QTL in reducing the severity of rust disease. So you can't protect your genotype by integrate only 1 or 2. Instead, just we need more number of minor genes or in combination of minor plus major genes just to reduce the effect of rust in the wheat population. So what is the relationship between grain yield and rust disease severity and their interactions? Because when we are breed for and when we are selecting for yield, there is a negative correlation always between yield and disease severity. So how we balance these two things before we go for the yield testing? Because yield testing is a very expensive exercise. So we need something, a population having a very good level of resistance before we are going to for yield testing. So as you can see, there is a yield disease severity negative correlation, which means higher disease severity means generally low yielding, which means the yield will be affected by the disease. So disease severity and genotype by environment, always a positive association, which means greater disease pressure often increase genotype by environment interaction by altering genotype ranking. Because when you have a resistance genotype, you will have very high yielding, and then when you have high disease severity, you will have low yield advantage. And the yield genotype by environment magnitude also different, and it's also environment dependent, and this very strong interaction reduce the predictability of yield performance across environments. Especially this is one of our main challenge in our breeding program. Just when we are applying genomic selection, this susceptibility affect a lot our prediction accuracy. So that's also one of a major challenge. And also when you are applying genomic selection for disease resistance, That's also related with the pathotype difference. So when you have different pathotype in every year, there will be different accuracy across a year. So that's also another challenge in our breeding pipeline. So this is just to give you how the grain yield and rust disease behaving for the genotype, environment, genetic architecture, primary drivers, which means for the interaction, and also the breeding target, what should look like for grain yield and disease resistance. So how can we best support the African wheat growing target population? As I mentioned before, there is a very good high yield correlation between CIMMYT, Mexico, and different part of the world, including Africa. But the disease correlation, especially the UG99 for stem rust, is still missing. So we need this component, because once we have a variety having a very good high yielder, but that will not taken by the farmers due to the susceptibility, because especially in Africa we are targeting smallholder farmers and resource poor. So this combination affect the adoption rate of our genotype or germplasm in the field. So what we need, both high yielding plus disease resistance, just to deliver to the farmers. So based on that principle, the East African wheat breeding pipeline, we call it Breeding Pipeline 5, established in 2022, just to leverage the genotype by environment interaction in the local condition. So we have different target product profile, and one of the major driver for that, for example, seed color is major trait, for example, in Ethiopia and also in Kenya. For example, in Kenya, farmers more prefer red seed market segment, but in Ethiopia, farmers are looking always the white seed market segment instead of red. But the red seed market segment in Kenya, especially that link with post sprouting, and also there are some resistance gene linked with that. So our breeding program is based in Kenya, Ijoro, but we are distributing all those crossing and advancing material into different other African countries. They are receiving our material for local test, and also we are using those data for our breeding optimization. At the same time, they are using those material for release for their local breeding program. And this breeding, the East Africa breeding pipeline, is a collaborative breeding program with Kenya KALRO, we call it Kenya Agriculture Livestock Research Organization, and EIR, Ethiopian Institute of Agriculture Research. So this is a breeding pipeline run by these three different institutions. So far we have very good interaction and also key outcome like modern breeding operation in the region. We are sharing different technologies and also application and enhance disease resistance, especially as you can see this one, for example, last year phenotyping from Mexico breeding pipeline and the East African breeding pipeline. In the right side, PC means Marcela chica from Mexico. This is stage one material around 4,500. And also we have around 1,500 from the East Africa breeding pipeline. As you can see, the disease severity, most of the material, this is the percentage, so more than 80% of the material is less than 5% disease severity for yellow rust, and also almost 60% of the genotype is less than 5% severity for stem rust. So this is a very good indicator how this locally adapted and also locally selected material performing better in terms of disease resistance. So we will expect the same thing for the yield performance across different locations, because this is a very early stage, and then now we are going to planting the stage one material in the field just to see how the performance also in terms of yield. But in terms of disease, they looks much better. And the other advantage, accelerated varietal release. We are also supporting our nurse partner just to release a variety as quick as possible, and strengthens regional capacity of the different breeding national program. So that's also our main objective, just to based here in East Africa, the wheat breeding pipeline 5. So in overall, our regional breeding pipeline is targeting to strengthen our national program to successfully deploy climate resilient, rest resistance with variety to farmers who need them the most, especially the resource poor farmers. So our ambition is just to increase the yield by 15% by integrating genetics and agronomy, and accelerate varietal release, quick release of varieties to farmers. That also one of the mitigation strategy for rust disease in Africa, because if you are not releasing varieties as quick as possible, the resistance gene will be broken within a few years. So there will be some shortage of varietal replacement. So one of our target is just to accelerate varietal release, and then most of the variety uh, uh, will be distributed to the farmers within a short period of time. And other main objective is a stronger national program. So once they have very good breeding program, they will run all their activities by themselves. So in the future, our approach is by using historical data, including disease and yield, and also environmental cover rate. Now this is the era of AI, so we will predict the future climate and also the future proof climate proof breeding lines to the farmers. So when we are talking about in Africa, not only the biotic stress, as I mentioned before, there is also biotic stress, especially heat and drought. So we need all those components together just to release the varieties to the farmer's hand. This is one of the impact in Ethiopia, for example. Now Ethiopia is self-sufficient in wheat. That's also linked with the initiative of the government. So one of my message here is there is a high genetic gain, as you can see here in Ethiopia since 2000, and that is achieved by a combination of genotype, environment, management, plus political commitment, because this is also very important for the wheat production in a given country. So political commitment is very, very essential. So this is one of the indication of political commitment from Ethiopia. Capacity building is also very important, just to bring the next generation of wheat breeder, wheat pathologists, wheat agronomists. So we are also giving a number of capacity building training here in Kenya and also in Ethiopia, by bringing people from other African country and also South Asia. And the other most important part for rest breeding, not only for field phenotyping, we need also phenotype material in the greenhouse. We call it seedling test. That indicates the major or minor gene combination of the material, how once we combine this seedling test with field testing. So we know which material is carrying a major gene, which one is carrying minor gene combination in the resistance background. So this is also one of our main activity here in Nairobi, in Njoro, Kenya. So this is my final slide. So what is the take home message? GBI is not a biological opportunity, not merely statistical noise. So we need to exploit this important opportunity, because when we are talking about GBI, for example, our Mexico breeding pipeline is breeding for the bigger agroecologies in South Asia and other part of countries, but the disease component is still very important here in Africa as well. So we are exploiting this one in just to advance material for specific adaptability. Grain yield and rest resistance are influenced by different biological process, and their exhibit different GBI pattern. As I mentioned before, the GBI pattern is not similar for both of them. They are differently affected by environment, differently affected by pathogen, differently affected by management. Yield stability alone is insufficient if disease resistance is unstable, especially when there is a high disease pressure area like East Africa. And durable rest resistance without competitive yield is unlikely to achieve farmers' adoption. That's also very important. So there should be some threshold level just to combine both yield stability and durable rest resistance. So always we are working on durable rest resistance part at early stage when we are advancing our material from different filial generation. We are doing this selection in high hotspot area just to remove all those susceptible and then to advance the resistance one. And then finally we are doing the yield test stage 1, stage 2, stage 3 just to pick the baseline across different years and location. So the future breeding program should integrate multi-environment phenotyping, as I mentioned before, not only for rust. We are also targeting Septoria, Fusarium, and other disease. Pathogen surveillance is very important, especially when we are dealing with rust. And genomics, especially genomic selection, when we need to incorporate more QTL or minor allele effect into the background of the breeding population. Environmental characterization and digital breeding also very important, especially digital breeding just to increase the data point for decision purpose. So my final statement, future genetic gain depend on integrating yield potential, durable rust resistance, and an understanding of G by E interaction into modern wheat breeding. That will help a lot farmers, the wheat farmers in Africa, especially small scale farmers and resource limited farmers, just to give them a good genotype combining both yield potential and also durable rust resistance. Thank you very much, and thank you for your listening, and I'm happy just to receive any question. Thank you very much.
Thanks so much, Professor Zerihun, for a brilliant presentation. It's a pleasure to learn about the wet breeding strategy adopted by CIMMYT. It's really a challenge to select genotypes that are rival yielding and resistant to disease and stable. Yeah. And we will now move on the questions. Innocent Unzimai essay. Hi Tadesse, please help to explain the difference between target population of environment TPA and breeding zones, perhaps in the context in Kenya. And one more moment, the question complement this. The Professor Dr. João Batista Duarte, while talking Dr. Tadesse acknowledgement, a good question for Dr. Zumai, I ask for pedagogical reasons that will also include your conceptual understanding of a mega environment.
Okay, yeah, just when we're doing the breeding, we are not breed for everything or just to exploit the specific adaptability of the wheat population. We need to classify our target environment into different classes. For example, during my presentation, as I mentioned, the mega environment is based on some criteria. We already classify the area of wheat production for targeting. So those mega environment related with our international nursery. So where our international nursery targeting different mega environment. So we have different list of international nursery. So those international nursery, for example, targeting high heat tolerant or moisture stress tolerant or high yield potential area. So based on that, we are classifying those things into different mega environment. We use some criteria just to delegate or just to classify those environment into subclass. But nowadays we are working on based on target population environment that's more advanced by integrating different climatic and also some multi-environmental analysis just to classify exactly how those environments are looks like different. Because for example, when I take one of the example in South Asia, we have three different target population environment. We call it target TPE1, target population environment 1, target population environment 2, and target population environment 3. So target population environment 1 is mostly high yielding environment, and also the temperature is not that much a big issue. And target population environment is a medium kind of agroecology, having heat and drought is an issue. And target population environment 3 is typically a wheat growing area having high high drought issue and also heat issue. So this is our different target population environment, and also our material also targeting for different. So when we are selecting our material for TPE1, always we are looking high potential lines. We are not considering maybe heat tolerant or drought tolerant. But when we are looking for TPE3, always we need to consider the yield potential plus high yield, high heat tolerant and drought tolerant traits. So these traits should be together when we are targeting that particular environment. So this is how we are classifying our target agroecologies as target population environment. Yeah.
Thanks for so much, Dr. Zerihun. Go to the next question. Camila Barros, in your view, what you wheat breeding looks like in 20, 30 years in terms of data, environment, and selection strategies?
Yeah, a very good question. Yeah, to be honest, it's very good question, and that's also my question sometimes. How it looks like after 20 or 30 years under this different climatic change. So the good part nowadays, just we have a number of new technologies coming up just to work more on the genetics part. So one of the strategy, for example, haplotype stacking, instead of stacking like different single genes, we can stack a number of different haplotype into one genotype and just to serve for different trade. And also now we are on the era of AI, so that will help us just to integrate different data point, which means from the field phenotyping, environmental covariables, and also even social covariables. So we can combine all those different variables into one just to predict and select the best material in the future. So now we are working on that side, but still it's very challenging in the near future because of this global warming, and also nowadays the yield is very affected by night temperature as well. So we need to work more aggressively just to ahead of those trade. Otherwise the wheat production will be in a very high risk condition if we are not working ahead of those trade.
Thank you so much, Dr. Tadesse. It's a real pleasure to have you with us today. We truly appreciate you taking the time to share your knowledge and experience with us. Tadesse, you are more than welcome to join your next lecture. Your next lecture will begin in just a few minutes, so we kindly ask everyone to move over to the next YouTube stream using the link available in the chat. We look forward to seeing you there. Thanks so much, and you see in a few minutes. Thank you, Dr. Tadesse.
Thanks so much, and have a good day.
Thank you.